Okay, so let's resume from where we left on the last live session. Um, so after introducing the universal quantifiers, it's good to know that um, they have a special precedence on all the uh, other logical operators. So they have actually the highest precedence. So if you have this sentence for every x, p of x, or q of x, then in this case, the default reading is that for every x, p of x, or q of x separately. And the q of x is no longer under the scope of the universal quantifier, which means that this part here is does not have a meaning, does not have a meaning anymore. Okay, you cannot evaluate it to true or false. Okay, it's not a true. Q of x in general without a quantifier is not true, neither false, as we have discussed in earlier examples. So to avoid this misunderstanding, uh, let's use fully parenthesized formulas where you put for every x outside, and then you put the p of x or q of x inside the scope of the quantifier. Okay, so here we have the scope of the quantifier, universal quantifier for every x. So we have both formulas p of x or q of x under the scope of this quantifier. And now this makes sense because what's meant by this sentence is that for all your elements under consideration, the property P of P is true for them, and the property Q is also true for them. Sorry, or the property Q is true for them. So either P or Q. It could be both of them, of course. Um, so in this format, some means really something different. So on one hand, it's well formed. So the problem with this format here is that the final formula is not well formed in the first place. Okay, so we cannot talk about its meaning. Okay, it's not just that the meaning is different. Okay, but the problem here is that this sentence does not even have a clear meaning, or it's not well formed actually. Okay, because we are left with q of x with a without a quantifier beside it. We don't have neither for every nor that exists. So it's a common mistake to write for every x, p of x or q of x when you mean this. Okay, so please always use the parentheses. It also applies for the implication. Huh? So when you have for every x, p of x implies a q of x, then please add the parentheses on the outside. Okay. Um, okay, so let's play um, with some examples to see how do we translate from English to logic. So translate the following sentence into predicate logic. Every student in this class has taken a course in Java. Okay, so let me help you in developing your um, um, let's say ability to translate from English to predicate logic. So the first thing that you have to think about is the predicates. So you have to define the predicates yourself, so one or more, and you have to also specify the domain of the variables that you have in hand. Okay. Um, so and then you chase the words for every and that exists in your sentence, and you translate them into quantified expressions, quantified predicates. So here we are talking about students, particularly students in this class. Okay, so we have a domain reduction to talk particularly about students in this class, and we have the fact that they have taken a course in Java or not. Okay, so it really depends on what you want to do. So you can consider the domain to be d of x to be persons in general, okay? And then you can use a predicate called a student, okay, to narrow down your choices, okay, of persons. with which you are concerned to those who are students in your class or students in general. Okay, so here we can say that student of X is true if and only if X is a student. Okay, you can also say that class of X means that X is in this class. Okay, and you can use a third one to say that X has taken a course in Java. Um, you can use Java of X to say that X has taken a course in Java. Okay, like even the third one actually could say that has taken. You could use the predicate has taken X a course C. Okay, by specifying that D of C is the set of courses. Okay, um, and add to it the fact that C is equal to Java. Okay, or is a Java course as a predicate that returns true if C is a course in Java. Okay, so you see, it's really flexible, and this is normal actually. Okay, maybe some students are thinking now that even the class thing can be cut into two separate pieces. So is in or is registered in. Okay, so you could split it into two different facts. Is registered in a certain student X a course C. Okay, um, and C is equal to uh, this course. I don't know which one they are referring to. Okay, um, something like that. Okay, so for example, CMPS211, something like this. Okay, so you can really invent or come up with your own predicates. Okay, but now the question is, where do you stop? And which version do you choose? Okay, so as in any other modeling effort, um, usually when you model real life scenarios with a certain formalism, uh, there is no one single constraint, but there are simply recommendations. So if you add too much details and too much predicates, maybe they are not needed to express your facts and to finally reason about your properties. Okay, and sometimes you cannot reason because you have certain hidden details. Okay, so just remember, from the beginning we motivated the use of predicate logics because we couldn't express something like BBC said that it's raining today and CNN said that it's not raining today. Okay, so if we add rain and not rain simply as proposition, we will end up having a conflict. But if we add the predicate say, or announce, okay, and we add a conjunction, well, we have something and something else, and they can co-live together, okay, without any conflict. Okay, so in the first place, the introduction of predicate logic was to actually uh, uh, allows us to allow us actually to reason about more complex situations, and instead of replacing whole declarative sentences with simple letters p not p, rain not rain, etc., we wanted to introduce more functions and correlations between objects and facts about them. So which version to choose? I will show you with the various versions how we can get to our to a correct answer. Okay, and still we have something kind of like equivalent. So let me just skip um, the slide and then I will get back to it. So in the first version, if we keep it uh, as general as possible, so I'm gonna consider student of X to be particularly X is a student in this class. Okay, I'll consider the easiest version. Okay, and Java of X, okay, to be X has taken a course in Java. Okay, And in this case, the domain of X could be anything you want, actually. It could be persons or students in general. Okay, so persons or students in general. Okay, in general. And in this case, what this sentence is saying is that for every element X, for any person or student in general at AUB, let's say, or even worldwide, um, if X happens to be a student in this class, okay, a student of X, which means X is a student in this class, necessarily Java of X must also be true, okay? That student must have taken a course in Java, okay? So do you see? Just pause, think about it, and if you came up with your own versions, okay, then just compare them to this one. One of the famous versions that students come up with is the following. They would say student for every X, a student of X and a Java of X, okay? But let me show you why this is not a good, this is not equivalent to the sentence given above. And this is not an accurate translation of it. Because the exact translation of this one is as follows. So every student, so this one is every student in this class, or actually, in this case, X is ranging over the set of persons or students in general. So we have to say that every student, okay, or person, and not necessarily in this class, um, is a student in this class. So every student is a student in this class because this property is true for that X is a student in this class and has taken a course in Java, and which is not really okay. So it's not the case that every person or every student in general, or not even every student at AUB is a student necessarily in this class and has taken a course in Java. It's not the case, okay? So when you use the universal quantifier, typically you would use with it when you're generalizing rules about universal facts, you would often use an implication because it states that in case this property applies to the elements you're arranging over them, then this property must necessarily hold for them. Okay, so please avoid the version with the and unless you are sure that it's correct. Okay, so sometimes you have um, certain correct translations, but just make sure that really both the properties apply and they apply to all the elements in your domain. If your domain is all the students in the university, then both properties must be correct for them. So let me show you how to translate this if we restrict the domain. So if you restrict the domain of X to be the students in this class and not students in general and not persons in general, okay? So if domain of X is students in this class, well, actually, you don't need to express a student of X anymore, okay? Because all your X's are students in this class. You just have to talk about their property, Java of X, where this means that X has taken a course in Java, okay? So, and in this case, all that we can say is that every element in this set, so for every X in this domain D of X, we simply have the fact that Java of X is true, okay? It's much simpler, but it's hiding plenty of facts about X, okay? So if you want to combine it with other facts about students which are not in this class yet, they are registered at the same university, who are in the course and in the club XYZ, etc. So you clearly need to clarify this property, whether they are student in this class or in another one, they are member in a club or another one. So it really depends on the problem in that you have in hand that you are trying to model. Okay. Um, Usually the golden rule is to introduce more predicates, okay, um, um, when actually more details, okay, are needed, okay, details are needed, and where you have actually certain segregation of the elements of your domain um, um, between multiple subsets of elements, okay? And in this case, actually, it also happens when you have more general domains, okay? Um, with more specific subdomains. Okay, so once you generalize the domain to reach all the set of persons, where the person can be a student or not, whether students can be in this class or not, okay, and so on and so forth, then as much as needed to generalize over the set of all the elements, okay, in this case, I think you will generalize the domain, but you will also introduce more predicates to specify the particular classes or subsets of this general domain. Okay, is it clear? I hope it is. You can pause the video. You can reconsider the other readings and try to reformulate them on your own. Okay, so good. So if you decide on the domain U and consider all the students in this class, then you can say for every x j of x. But if you restrict it, if you actually generalize the domain to all people or students in general, then you need to introduce a new predicate x of x, and you need to specify this in this way. For every x student of x implies j of x. Okay? And why this is not correct? Actually, I already told you, if you say this, it means that all people on Earth, they are students in this course and they have taken a course in Java, which is a much stronger claim. We don't have it here. We only have this implication, this conditional. Just if you pick up a person, just in case they are a student in this class, then they necessarily would have taken a Java course. And by the way, with implications, if you have for every x a certain property of x implies a q of x, um, it's it's um, it's nice to have such combination of for every n implications, because just in case none of the elements have p of x, then it's not necessary to have q of x at all. Okay, so if the premise is false, okay, this implication would be true, this rule would be fulfilled, even if all the qx's are false. Okay, well, you can have some of them being true, but it's not a big deal, even if it's false. Okay, it's only saying that just in case p of x is true, then necessarily q of x must be true. Okay, good. Um, in the second example, we have an existential operator. So I highly recommend that you pause the video and you think about it on your own before you get the solution. And actually, in the same way, it depends on the domain. So if the domain is all the students in this class, then you have just to say that some of them have j of x. Okay? But actually, what if you generalize the domain to consider all people? Well, then in this case, you need to say that there are some people who are students in this class. Okay? And do we use implication here or conjunction? So unlike the previous example, the implication marries well with the actually existential quantifier. So usually we would say there are some people who are students in this class and they have taken a Java course. Okay. If you think about the implication version, okay, so I think this is sad here. okay, in this version. If you think about the implication version under the scope of existential quantifier, you will notice that this is a very weak fact about the reality. What this sentence is saying is that there is some person uh, or persons such that just in case there are students in this class, then they necessarily have taken a Java course. Okay, good, but it does not mean that there are some students in my class. Okay, in the original sentence, it is saying that some students in this class, as if there are already some students. Okay, so student of x0, okay, must be true for certain x0. So the sentence is saying at the same time that there are some students in my class. My class is not empty. So some students in this class have taken a course in Java. It means that there are really some of them, and they have taken a Java course. Okay, but with this implication, it's a very loose reality. It's a very loose fact. It does not oblige us actually to have students in my class in the first place. So if it happens that for all people on Earth, no one of them is registered in my course, then, well, this existential predicate logic formula would be true, although none of them maybe they took the Java course. It could be that some of them they also have taken a Java course, okay, but we don't care anymore, because for all, if it's the case that no people are registered in my course, then it does not really matter. The implication would be correct for all of them, even though they have taken or not a Java course. Okay, so it could be that all of them have not registered my course and all of them they didn't take a Java course. So do you see? Okay, it's a completely different meaning. So more examples that you can check mostly on your own, but I will be skimming them with you. So if you say some students in this class have visited Mexico, um, if you consider M of X to be have visited Mexico and S of X to denote X is a student in this class, then if U is the set of all people, in this case, you can say that there exists an X such that student of X and M of X. Okay. Again, if you restrict the domain to only students who have registered your course, then in this case, you can say that there exists an X such that M of X. Okay, as simple as that. So every student in this class has visited Canada or Mexico. You have to introduce two predicates as C of X and M of X. And in this case, you can say that for every element X, if S of X is true, if X is a student in my class, in this case, necessarily M of X or C of X must be true. Okay, so I hope that this gives you a clearer idea now. Now we have two slides, 15 and 16, that would allow you to entail equivalences in predicate logic. So usually you can use all the equivalence rules that you knew about in classical propositional logic, but you can add to them the following. So statements involving predicates and quantifiers are typically logically equivalent if and only if they have the same truth values. For every predicate substituted into these statements and for every domain of discourse used for the variables in the expressions, the notation as is equivalent to t indicate that as and t are logically equivalent. And an example is the following. If for every element in your considered domain, the property P and the property Q are both true for your elements, then you can also say that for every element in your domain, P is true for them, and for every element, Q is true for them. Okay. And why can we prove this? Because actually, on the next slide, we will show you how to think about the quantifiers as conjunction and disjunctions. Well, actually, If the domain is finite, then a universally quantified proposition is equivalent to a conjunction of propositions without the quantifiers, and an existentially quantified proposition is equivalent to a disjunction. For example, if you consist of the integers 1, 2, 3, then when you say for every x, p of x is true, this means that p of 1 and p of 2 and p of 3 are true. Okay? But when you say that there are some elements such that p of x is true, then all that you are sure of is that p of 1 is true, or p of 2 is true, or p of 3 is true. You don't know which one of them. But of course, you know that this disjunction becomes false if all of the elements do not have P, okay? So they do not satisfy the property P. Okay, for this disjunction to be true, at least one of them must be true. It could be more than one of them. Good. And by the way, this is how you can prove the property on the previous slide. Once you transform this into P of x0 and P and the Q of x0 is true, and the same P of x1 and Q of x1 is true, up to the last element in your set, which is actually P of xn and Q of xn is true. Okay, so you can rearrange the elements actually, since it's a disjunction of a conjunction of conjunctions. Well, you can rewrite it as P of x0 is true, and P of x1 is true, and P of x number n is true, and Q of x0 and Q of x1. I think you got the idea, okay? So I'm just rearranging the terms since the and is associative and commutative, okay? And the Q of xn. And the first one is nothing, okay? So what this is equivalent to, so the first one is nothing but for every x, p of x, because p of x is true for all the elements. And the second part of this equation is, or this formula is for every x, q of x, because q of x is true for all the element x, okay? So do you see how can we prove equivalence between universal quantifiers or existential quantifiers? So just by replacing them by their definition over a finite set of elements from x0 up to a certain xn, okay? And this is what we want you to learn here. So even if the domains are infinite, you can still think of the quantifiers in this fashion, but the equivalent expressions without the quantifiers will be infinitely long. So you can talk about the conjunction of p of xi for every xi, something like this, okay? And the disjunction of q of xi for every xi, something like that, okay? So good. Now we have to learn about the negation of the quantified expressions. I already evoked the concept with you, so a few slides ago and during the live session of Monday. So when you consider this expression, every student in your class has taken a course in Java. Here actually, X taken a course in Java with the domain being the students in your class. If you negate this statement, it would be something like, it's not the case that every student in your class has taken a course in Java. Okay, so it's not the case that all the students in your class has taken a course in Java. Okay, it's not the case that for every x, j of x, and this is equivalent to the fact that for every x, j of x is false. Okay, but how this correlates to the existential operator? Well, actually, if it is not the case that all of the students have taken a course in Java, this means that you're sure that some of them, at least one of them, did not take a course in Java. Okay, so do you see how these two formulas correlate? Let me show it to you syntactically now. If you are convinced with the meaning, syntactically it's really beautiful. Since the for every is the dual of the there exists, well, what happens here is that the negation, to get inside the quantifier, it flips, okay? It flips the quantifier to its dual and then gets um, uh, inside it, okay? So while walking over the quantifier, it flips it and gets inside. And even when we learn about nested quantifiers, when you have several nested quantifiers, you see that the same concept applies. So we have there exists x such that for every y friend of xy, okay, for example, and you want to negate it, okay, well, this becomes equivalent to for every x, there exists at least one y such that not f of x and y. And let's think about it. If someone is saying that uh, there is a person who is a friend with everyone, if someone wants to refute his claim or her claim, so if someone wants to show us that it's not the case that there is a person such that that person is a friend with everyone else, well, that person, that new let's say entity has to show us that for every person there exists at least one other person, so that these two persons are not friends with each other. Okay, so it's 100%. So when you want to get the negation inside, okay, you flip the quantifiers on your way. Okay, so this is the general concept. Good. Let's consider another example. If someone said that there is a student in this class who has taken a course in Java, well, the negation of this, it's not the case that there is a student in the class who has taken a Java course. It's not the case that there is a student. And this means that, okay, so it's not the case that someone took a course in Java. Well, this is 100% equivalent that all the students did not take a Java course. Do you see that once again, when the negation, when you want to get the negation inside, you should flip the quantifier, okay? Yeah, so in this case, it means that every student in this class has not taken a Java course. Good, so you have this recap table, and now you can apply these concepts to study the last example, the last examples that are given in this deck of slides. We can discuss them later on Thursday together if needed, okay? But I think that you will understand them easily on your own, okay? So just check these examples very quickly with the answers not revealed, and then we will discuss them together on Thursday. Thank you for your listening, and see you in the next video about nested quantifiers, and then the last one about inference.